Picture this: a single point, smaller than an atom, holding all the energy of existence. Then, in less than a blink, it explodes into being. But here's the twist: that famous Big Bang wasn't the real showstopper. Right after, something far stranger happened: an expansion so fast it makes light look slow. Space itself stretched like a cosmic rubber band, smoothing the universe into the vast stage we know today. This is cosmic inflation, the universe's best-kept secret, and without it, you, me, and every star we see wouldn't exist. What if I told you scientists are still uncovering how this split-second event shaped reality itself? Stay with me, because by the end of this journey, you'll see the cosmos and your place in it in a whole new light. Now, let's untangle two of the biggest ideas in cosmology: the Big Bang and cosmic inflation. At first glance, they might seem like the same event, but they're actually two distinct chapters in the universe's origin story. Think of it like this: if the Big Bang was the spark that lit the cosmic fire, inflation was the sudden gust of wind that blew it into an inferno. The Big Bang marks the moment when all the energy and matter in the universe burst into existence from an unimaginably dense point. But here's where things get wild. Immediately after that initial explosion, we're talking within a fraction of a second, cosmic inflation kicked in. This wasn't just rapid expansion, it was space itself stretching faster than the speed of light, doubling in size over and over again in less time than it takes to blink. Why does this matter? Without inflation, the universe as we know it wouldn't exist. The Big Bang created the raw ingredients, but inflation was the cosmic chef that mixed them perfectly. It smoothed out the universe, ironing out any wrinkles in space-time so that temperatures became nearly identical everywhere, something we still see in the cosmos today. It also stretched tiny quantum fluctuations into the seeds of galaxies, stars, and eventually us. But here's the key difference: while the Big Bang was the beginning of everything, inflation was the brief but extraordinary growth spurt that shaped everything. It lasted only a sliver of a second, yet its effects are written across the entire sky. Next time you look up at the stars, remember, their existence hinges on that fleeting moment when the universe expanded faster than light itself. And the craziest part, we're still piecing together exactly how it all happened. What's even more mind-bending is that inflation didn't just happen once. Some theories suggest it could still be happening right now in distant corners of the cosmos, creating bubble universes with entirely different laws of physics. But that's a story for another moment, one that takes us even deeper into the mysteries of our cosmic origins. But how did scientists even come up with the idea of cosmic inflation? Let's rewind to the late 1970s, when a young physicist named Alan Guth stumbled upon a revolutionary concept that would change cosmology forever. At the time, scientists were grappling with two baffling mysteries about the universe: the Horizon Problem and the Flatness Problem that the standard Big Bang theory simply couldn't explain. Guth's breakthrough didn't just solve these puzzles, it reshaped our entire understanding of the cosmos. Picture this: the universe as we observe it is strangely uniform. No matter which direction you look, the temperature of the cosmic microwave background, the afterglow of the Big Bang, is nearly identical, down to a fraction of a degree. But here's the catch: according to the speed of light, there hadn't been enough time since the Big Bang for heat to spread evenly across such vast distances. This is the Horizon Problem. How could regions of space that were never in contact with each other end up at the same temperature? It's like walking into two separate rooms on opposite sides of the planet and finding them set to the exact same cozy temperature, even though no heater could have connected them. Then there's the flatness problem. The universe's geometry appears perfectly flat, meaning parallel lines stay parallel forever, and the angles of a triangle add up to exactly 180 degrees. But for this to be true, the universe's density at the moment of the Big Bang had to be fine-tuned to an absurdly precise value, like balancing a pencil on its tip for billions of years. Even a tiny deviation would have caused space to either collapse in on itself or expand so rapidly that galaxies could never form. The odds of such perfect balance seemed impossibly slim. Enter Alan Guth. In 1980, while working on an unrelated problem involving magnetic monopoles, he realized that if the universe underwent a brief period of exponential expansion, a trillionth of a trillionth of a trillionth of a second after the Big Bang, it could solve both problems in one stroke. Inflation stretched space so rapidly that regions now separated by billions of light years were once close enough to equalize their temperature, explaining the Horizon problem. It also smoothed out any initial curvature, like stretching a crumpled sheet of paper until it appears flat, resolving the flatness problem. Guth's theory wasn't just elegant, it was testable. It predicted specific patterns in the cosmic microwave background, which later observations confirmed with stunning accuracy. But here's the twist: Guth initially called his idea a spectacular realization, only to later discover a critical flaw. The mechanism he proposed would leave the universe empty and cold after inflation. It took other physicists like Andre Linde and Paul Steinhardt to refine the theory into what we now call new inflation, where the Inflaton Field decays gradually, reheating the universe into the vibrant cosmos we see today. What's remarkable is how a single insight, born from wrestling with unanswered questions, could unlock so many cosmic secrets. Inflation didn't just patch up gaps in the Big Bang theory. It revealed a universe far more dynamic and mysterious than anyone had imagined. And as we'll see next, those tiny quantum fluctuations it amplified didn't just vanish, they became the blueprint for everything from galaxies to you watching this video. Now, let's take a closer look at the Horizon problem, one of the biggest head-scratchers in cosmology before inflation came along. Imagine two friends standing at opposite ends of a football field, each holding a cup of coffee. Without any interaction between them, you'd expect one coffee to be hot and the other cold, depending on how long they've been standing there. But what if both cups were exactly the same temperature, down to the tiniest fraction of a degree? That's essentially what we see in the universe. The cosmic microwave background, the oldest light we can observe, shows nearly identical temperatures in all directions, even in regions so far apart that light couldn't have traveled between them since the Big Bang. Here's why this is so puzzling. According to Einstein's theory of relativity, nothing can move faster than light. So, if two patches of the early universe were too far apart for light or heat to have shuttled between them, how did they reach thermal equilibrium? It's like those two friends with their coffee cups never met, never shared a thermos, yet somehow their drinks are perfectly matched. The standard Big Bang model couldn't explain this, and it left scientists searching for a mechanism that could synchronize temperatures across cosmic distances without breaking the rules of physics. This is where cosmic inflation delivers its masterstroke. The theory proposes that in the first sliver of time after the Big Bang, space itself expanded faster than the speed of light. Now, this might sound like a violation of relativity, but here's the key distinction. It's space that's stretching, not objects moving through space. Think of it like dots on a balloon. As you inflate the balloon, the dots move apart, but the dots themselves aren't zipping across the surface. They're being carried apart by the stretching fabric. Inflation suggests that regions of the universe, now billions of light years apart, were once close enough to exchange heat, like neighbors passing a cup of sugar. Then, in a fraction of a second, exponential expansion pushed them far beyond each other's cosmic horizons, locking in that uniform temperature. The elegance of this solution is breathtaking. It doesn't just hand-wave the problem away. It provides a precise mechanism rooted in the physics of fields and energy. By stretching space faster than light could traverse it, inflation ensured that the entire observable universe emerged from a tiny, causally connected patch. That's why we see such stunning uniformity in the cosmic microwave background today. And here's the kicker, this wasn't just a theoretical fix. Inflation made specific predictions about the patterns of temperature variations we'd find in that ancient light. Predictions later confirmed by satellites like the Cosmic Background Explorer and the Planck mission. What's truly mind-blowing is how this brief burst of hyper-expansion didn't just solve the horizon problem, it set the stage for everything that followed. Those minuscule temperature differences, frozen during inflation, became the seeds for galaxies, stars, and ultimately us. Next time you look up at the night sky, remember, the vast, seemingly disconnected cosmos was once intimately linked, and inflation is the invisible thread that stitched it all together. But the story doesn't end here. Another puzzle, the flatness problem, awaits its own revealing twist. Now, let's turn our attention to another cosmic mystery that inflation elegantly unravels, the flatness problem. Picture this, if you were to measure the angles of a triangle drawn on a sheet of paper, they'd add up to 180 degrees, just as geometry class taught us. But if you drew that same triangle on a globe, the angles would exceed that sum because the surface is curved. The universe, it turns out, behaves like that sheet of paper. It's astonishingly flat on cosmic scales. And that's weird. Here's why. According to general relativity, the shape of the universe depends on its density. Too much matter and energy, and space curves inward like a sphere, eventually collapsing in a big crunch. Too little, and it curves outward like a saddle, expanding forever into thin emptiness. But our universe sits right on the knife's edge, a Goldilocks balance where the density is just enough to keep space almost perfectly flat. The odds of this happening by chance are like rolling a billion-sided die and landing on the one number that keeps the cosmos from either imploding or dissipating into nothingness. Before inflation, this fine-tuning was a glaring puzzle. If the early universe had even a tiny bit more or less density, that curvature would have magnified over billions of years. Imagine blowing up a slightly wrinkled balloon. As it expands, those wrinkles become massive canyons or towering ridges. Yet when we look at the universe, we see no such dramatic curvature, just a vast, smooth expanse. How inflation's answer is as simple as it is profound. That hyper-fast stretching didn't just synchronize temperatures, it ironed out any primordial wrinkles in spacetime itself. Think of it like zooming in on a crumpled piece of paper with a microscope. At first, the folds look jagged and dramatic, but as you magnify the image, the creases stretch until they're too faint to see. Inflation did that to the universe by expanding space by a factor of at least 10 to the power of 26 in less than a trillionth of a second. It took any initial curvature and stretched it to near perfect flatness. What we perceive today isn't a cosmic coincidence, it's the natural outcome of that relentless smoothing. The evidence for this is written in the cosmic microwave background. Precise measurements show the universe's density is within 1% of the critical value needed for flatness. Inflation doesn't just explain why we observe this, it predicts it. And here's where it gets even wilder. Without inflation, the universe would have needed to be fine-tuned to 1 part in 10 to the power of 60 at the Big Bang to appear this flat today. That's like hitting a bullseye the size of a single atom on a target larger than the observable universe. Inflation replaces that absurdly unlikely scenario with a straightforward physical process. Rapid expansion flattens spacetime, full stop. But inflation's brilliance doesn't stop at solving old puzzles. It reshapes how we see the cosmos. That flatness we measure, it might not be the whole story. Just as the Earth feels flat beneath our feet but is really a sphere, the universe could be far larger than we can observe, with our flat patch merely a tiny fraction of a grander, possibly curved cosmos. Inflation hints at this humility. We're not seeing the universe's true geometry, just the smoothed-out aftermath of its explosive youth. So the next time someone marvels at the night sky's vastness, remember, its apparent flatness isn't an accident. It's a fossil of those first frantic moments when space itself was stretching beyond imagination, leaving behind a stage perfectly set for galaxies, stars, and life. And waiting just beyond this revelation, the quantum quirks that would one day weave the cosmic web we call home. Here's where the story of cosmic inflation takes a truly mind-bending turn. While inflation was stretching the universe to unimaginable scales, something extraordinary was happening at the quantum level, a process that would ultimately shape everything we see in the cosmos today. At the heart of this phenomenon are quantum fluctuations. In the microscopic world, particles and fields are never perfectly still. They jitter and dance due to inherent uncertainty, popping in and out of existence like bubbles in a fizzy drink. Normally, these fluctuations are tiny and fleeting, but during inflation, space expanded so rapidly that these quantum wrinkles didn't just vanish, they were stretched to cosmic proportions. Imagine blowing up a balloon with tiny dots drawn on its surface. As the balloon inflates, those dots grow into vast patterns. Inflation did the same thing to space-time, magnifying microscopic ripples into macroscopic undulations. These stretched-out quantum fluctuations became the seeds of all structure in the universe. Slightly denser regions where the Inflaton Field had a tiny extra bump ended up with a bit more gravitational pull. Over billions of years, that extra tug attracted matter, causing gas and dust to clump together. The result, galaxies, galaxy clusters, and the vast cosmic web we observe today. Meanwhile, slightly less dense regions became the great cosmic voids, empty stretches between the threads of this grand tapestry. The cosmic microwave background gives us a snapshot of these primordial fingerprints. Its temperature variations, tiny differences in the glow of the early universe, match the patterns predicted by quantum fluctuations stretched by inflation. These variations are minuscule, just 1 part in 100,000. But they're precisely the kind of imperfections needed to grow a universe full of stars and planets. Without them, the cosmos would be a featureless sea of uniform matter. No galaxies, no stars, no us. Here's the beautiful part. Inflation didn't just create these density variations, it fine-tuned them. The theory predicts a specific spectrum of fluctuations, one where smaller bumps are slightly more common than larger ones. And when scientists measure the distribution of galaxies and the CMB's patterns, guess what? They match inflation's prediction almost perfectly. It's as if the universe left us a breadcrumb trail back to its quantum origins. Yet inflation's quantum legacy goes even deeper. Some theories suggest these fluctuations might have created more than just matter. They could have spawned gravitational waves, ripples in space-time itself. If detected, these waves would be the ultimate smoking gun for inflation, a direct echo of the universe's tumultuous birth. So the next time you gaze at the night sky, remember, the galaxies above aren't just scattered randomly. They're the children of quantum uncertainty, stretched and sculpted by inflation's relentless pull. And hidden within their arrangement lies a secret, a whisper from the universe's first moments, telling us how the smallest of beginnings can shape the largest of destinies. But what powered this incredible expansion in the first place? To answer that, we'll need to meet the mysterious force behind it all, the inflationary field. Now let's pull back the curtain on the engine behind cosmic inflation, the inflationary field itself. Picture this as the universe's hidden fuel, an invisible energy that permeated every corner of space during those first fleeting moments. Scientists call this the Inflaton Field, a hypothetical yet crucial player in the cosmic drama. Unlike familiar forces like gravity or electromagnetism, the Inflaton Field had one extraordinary property. It generated a repulsive gravity, pushing space apart instead of pulling it together. Think of it like a stretched rubber band. The Inflaton Field was under immense tension, packed with potential energy. This energy didn't just sit idle, it acted as a kind of cosmic anti-gravity, driving space to expand at an exponential rate. For a fraction of a second, this field dominated the universe, stretching it from subatomic scales to something far larger than our observable cosmos today. But here's the twist. This rapid expansion couldn't last forever. Like all unstable systems, the Inflaton Field eventually reached a tipping point. As the universe cooled, the field began to decay, releasing its stored energy in a spectacular finale known as reheating. Imagine water freezing into ice. The phase transition releases latent heat. Similarly, the Inflaton Field's decay converted its potential energy into a fiery burst of particles and radiation. This process didn't just mark the end of inflation, it set the stage for the universe we recognize. The sudden influx of energy repopulated the cosmos with matter and light, effectively hitting the reset button on temperature and density. But what made the Inflaton Field so special? Its energy landscape held the key. Most fields have valleys, low energy states where they naturally settle. The Inflaton Field, however, was perched on a high energy plateau. As long as it stayed there, inflation continued. But quantum fluctuations eventually nudged it toward the edge, causing it to roll down into a lower energy state. This slow roll phase was critical. It ensured inflation lasted long enough to smooth and flatten the universe, but not so long that it left space completely empty. The details of this field remain theoretical, but its fingerprints are everywhere. The uniformity of the cosmic microwave background, the distribution of galaxies, even the very fact that matter exists, all point to an era when this mysterious field held sway. And while we've yet to detect the Inflaton directly, its legacy is woven into the fabric of reality. So next time you hear about the Big Bang, remember, it wasn't the whole story. The real cosmic magic happened thanks to this elusive field, a fleeting yet colossal force that shaped everything from the largest galaxies to the smallest atoms. And as we continue to probe the universe's deepest secrets, the Inflaton Field remains one of its most tantalizing mysteries. Turning our attention to the echoes of the early universe, we find one of the most compelling pieces of evidence for cosmic inflation, the cosmic microwave background, or CMB. This ancient light, a faint glow permeating all of space, is the afterglow of the Big Bang, now cooled to mere degrees above absolute zero after traveling for over 13 billion years. But within this seemingly uniform sea of microwaves lies a hidden blueprint, tiny fluctuations in temperature that hold the secrets of inflation's aftermath. Picture the CMB as a snapshot of the universe when it was just 380,000 years old, a time when matter and radiation finally decoupled, allowing light to travel freely. What's astonishing is how remarkably even this snapshot appears. Across every direction we look, the temperature of the CMB varies by less than 1/100%. This near-perfect uniformity is exactly what inflation predicts. Remember, the Inflaton Field stretched space so rapidly that any irregularities were ironed out, leaving behind a cosmos almost, but not quite smooth. Those minuscule temperature variations, called anisotropies, are the real smoking gun. Inflation tells us that quantum fluctuations in the Inflaton Field were stretched to cosmic scales during expansion, imprinting their signatures as slight density differences in the early universe. These density variations later became the seeds for galaxies and galaxy clusters, and they manifest today as the hot and cold spots we observe in the CMB. The math is breathtakingly precise. Scientists predicted the statistical pattern of these anisotropies based on inflationary theory, and when satellites like COBE, WMAP, and Planck mapped the CMB with unprecedented detail, the observations matched the predictions with staggering accuracy. One of inflation's most elegant successes is explaining the angular size of these fluctuations. Without inflation, the universe's geometry would leave distinct imprints on the CMB, either much larger or smaller hot and cold spots than what we actually see. Yet the patterns align perfectly with a flat universe, another prediction of inflation. It's as if the cosmos handed us a puzzle, and inflation provided the only set of pieces that fit. But the CMB doesn't just confirm inflation, it challenges us to refine it. For instance, certain large-scale anomalies, like the so-called cold spot, defy simple inflationary explanations, hinting at deeper mysteries. Could these be signs of a multiverse, or do they point to physics beyond our current models? The CMB keeps us humble, reminding us that every answer invites new questions. What's truly remarkable is how this faint microwave whisper, a relic of the universe's fiery infancy, serves as both a time capsule and a Rosetta Stone. It not only validates inflation's grand vision, but also connects the quantum realm to the cosmic stage. Every subtle variation in this primordial light tells a story of a fleeting field, a runaway expansion, and the birth of structure. As we analyze the CMB with ever greater precision, we're not just looking back, we're uncovering the fundamental architecture of reality itself, one microwave photon at a time. Now let's dive deeper into the cosmic microwave background, where another fascinating clue lies hidden, waiting to reveal even more about inflation's explosive beginnings. Scientists aren't just studying temperature variations in the CMB, they're also scrutinizing something called B-mode polarization, a subtle twisting of light that could carry the fingerprints of primordial gravitational waves. Imagine the early universe as a stormy ocean, with gravitational waves, ripples in space-time itself crashing through the fabric of reality. These waves, generated during inflation's frenzied expansion, would have left their mark on the CMB by polarizing its light in a distinctive swirling pattern known as B-modes. Detecting this signal would be like finding the cosmic equivalent of a fossilized footprint, direct proof that space-time was once stretched violently by inflation. Here's why this is so exciting. The inflationary field didn't just stretch space, it also jostled the quantum vacuum, producing gravitational waves with a unique spectrum. As these waves traveled through the universe, they subtly twisted the polarization of the CMB's photons, creating a telltale spiral pattern. Unlike other types of polarization, B-modes can't be easily mimicked by things like interstellar dust or galactic magnetic fields. If we find them, it's almost certainly inflation's doing. The search for B-modes has been a scientific roller coaster. Experiments like BICEP 2 initially claimed a detection in 2014, only for further analysis to show that cosmic dust might have muddied the signal. It was a reminder of how painstaking this work is, teasing apart a whisper of a signal from a universe full of noise. Yet, the hunt continues with projects like the Simons Observatory and future space missions, each armed with more sensitive instruments and better dust mapping capabilities. What makes B-modes so important is their potential to reveal the energy scale of inflation. The strength of these primordial gravitational waves would tell us just how powerful the Inflaton Field was, offering a rare glimpse into physics at energies far beyond what any particle collider could ever reach. It's like uncovering a hidden chapter of the universe's diary, written in the language of space-time itself. Of course, the absence of B-modes wouldn't spell the end for inflation. It might simply mean inflation occurred at a lower energy scale than some models predict. But if they're found, it would be one of the biggest breakthroughs in cosmology, confirming not just that inflation happened, but giving us unprecedented details about how it unfolded. So while the CMB's temperature variations have already given us a wealth of knowledge, B-mode polarization could hand us the ultimate key, a direct line to the universe's first moments written in light and gravity. And as technology advances, we inch ever closer to unlocking this cosmic cipher, one observation at a time. Here's the next section of the script, seamlessly continuing from where we left off. Now, let's take a step beyond our universe, because inflation might not have stopped everywhere. Some theories suggest that while inflation ended in our cosmic neighborhood, giving rise to the universe we know, it could still be happening elsewhere, endlessly birthing new universes like bubbles in a boiling pot. This is the mind-bending idea of eternal inflation, and it opens the door to something even wilder, the multiverse. Picture this. Inflation isn't a single event but an ongoing process, with space expanding so rapidly in some regions that new universes constantly pinch off, each with its own unique physics. In one bubble, gravity might be stronger. In another, atoms might not even hold together. Our universe, with its just right conditions for life, could be one lucky ticket in an infinite cosmic lottery. The implications are staggering. If eternal inflation is real, the laws of physics we take for granted, like the speed of light or the strength of electromagnetism, might just be local bylaws, not universal truth. Some universes could collapse instantly. Others might be filled with bizarre particles we can't even imagine. The multiverse wouldn't just be a sci-fi trope, it'd be a natural consequence of inflation's runaway expansion. But how do we test something so seemingly untestable? Surprisingly, there are clues. If our universe collided with another bubble early on, it might have left a faint imprint in the cosmic microwave background, a kind of cosmic bruise. So far, searchers for such anomalies haven't turned up proof, but the idea keeps physicists digging. Meanwhile, string theory adds another layer, suggesting these bubble universes could exist on higher dimensional branes, floating like sheets in a vast, unseen reality. Philosophically, the multiverse forces us to rethink our place in existence. Are we special, or just one outcome in an endless sea of possibilities? Some argue it's a cop-out, explaining fine-tuning by saying every possible universe exists. Others see it as humbling, a reminder that reality might be far stranger than we've dared to dream. Whether eternal inflation is true or not, the idea stretches our minds as much as inflation stretched the cosmos. And as we push the boundaries of observation and theory, we might one day find out if we're alone in existence or just one voice in an infinite cosmic chorus. Now, let's take a detour into the realm of string theory, a framework that might hold the key to understanding how inflation actually works at its deepest level. At first glance, string theory and cosmic inflation seem like two entirely different puzzles. But when you start connecting the dots, they fit together in a way that could rewrite our understanding of the universe's earliest moments. String theory proposes that the fundamental particles we know, like electrons and quarks, aren't really particles at all. Instead, they're tiny, vibrating strings, each oscillation giving rise to different particles. But here's where things get wild. For the math to work, these strings need to move through more than the 3 dimensions of space we experience. String theory suggests there could be up to 10 or even 11 dimensions, all curled up so tightly that we don't notice them in everyday life. So, how does this tie into inflation? Imagine these extra dimensions aren't just passive backdrops but active players in cosmic expansion. One leading idea is that inflation was driven by the dynamics of higher dimensional objects called branes, short for membranes. These branes could collide or interact in ways that trigger rapid expansion in our 3-dimensional space. Picture 2 sheets of paper floating parallel to each other in a higher dimensional void. If they collide and then separate, the energy of that interaction could be the spark that set off inflation, stretching our universe in an instant, and it gets even more intriguing. Some versions of string theory suggest that our entire universe might be a 3-dimensional brane embedded in a higher dimensional space. Other branes could exist nearby, each hosting their own universes with different physical laws. This ties back to eternal inflation and the multiverse idea. Those bubble universes might actually be other branes floating in this vast higher dimensional landscape. But here's the kicker. If string theory is correct and extra dimensions or brane collisions played a role in inflation, there might be traces left behind. For example, gravitational waves from those early moments could carry imprints of higher dimensional physics. future experiments like next-generation gravitational wave detectors could potentially pick up these whispers from the dawn of time. Of course, string theory is still speculative, and linking it directly to inflation is an ongoing challenge. Some critics argue it's too abstract to test, while others see it as the most promising path to unifying quantum mechanics and gravity, two pillars of physics that inflation straddles. Whether or not string theory ultimately explains inflation, it's fascinating to see how these grand ideas collide, offering glimpses into a reality far stranger than we ever imagined. This intersection of ideas doesn't just deepen the mystery, it opens up new ways to probe the universe's origins. And as we push the limits of theory and observation, we might just find that the answers lie woven into the fabric of dimensions we can't yet see. Now, let's step back and consider this: what if cosmic inflation isn't the only explanation for how the universe began? While inflation has become the dominant theory, it's not without its rivals, and some of these alternatives offer equally mind-bending possibilities. One compelling idea is the bouncing universe model. Instead of a singular Big Bang, this theory suggests our universe might be part of an endless cycle of expansion and contraction. Picture a cosmic accordion collapsing in on itself only to rebound again, over and over. In this scenario, the rapid expansion we call inflation could simply be the aftermath of a previous collapse, with the universe bouncing back into a new phase. Proponents argue this avoids the need for a true beginning, sidestepping the tricky question of what came before the Big Bang. But here's the catch: for a bounce to work, you'd need a mechanism to reverse gravity's pull during collapse, and so far that remains speculative. Then there's the variable speed of light theory, or VSL for short. What if light didn't always travel at its current breakneck speed? In the early universe, light might have moved much faster, allowing distant regions to reach equilibrium without requiring inflation's hyper-expansion. This tweak could solve the Horizon problem just as elegantly as inflation. But testing this is notoriously difficult. After all, the speed of light is now a cornerstone of physics, and altering it raises more questions than answers. Another intriguing alternative is conformal cyclic cosmology, championed by physicist Roger Penrose. He proposes that the universe doesn't bounce but instead resets, with each eon ending in a state so smooth and empty that it becomes indistinguishable from the beginning of the next. The evidence: Penrose points to mysterious patterns in the cosmic microwave background, which he interprets as echoes of a previous eon. Yet most cosmologists remain skeptical, noting those patterns could just as easily be statistical flukes. So why does inflation still reign supreme? For starters, it solves multiple puzzles: the Horizon problem, the flatness problem, and the origin of cosmic structure, all in one elegant sweep. Its predictions, like the spectrum of temperature variations in the CMB, match observations with uncanny precision. And while alternatives offer intriguing workarounds, they often introduce new complexities without the same explanatory power. Inflation isn't perfect; its fine-tuning issues and lack of direct proof leave room for doubt, but until a rival can match its breadth of success, it remains the best blueprint we have for the universe's explosive infancy. What's fascinating is how these competing ideas keep scientists honest. They remind us that even our most cherished theories must withstand scrutiny, and the cosmos might still have surprises up its sleeve. Whether inflation holds its ground or falls to a challenger, the quest to understand our origins is far from over. Now, let's take a closer look at one of the most persistent criticisms of cosmic inflation: the fine-tuning problem. Even though inflation has become the go-to explanation for the universe's early expansion, some scientists argue that it requires conditions so specific that they border on the improbable. Imagine setting up a row of dominoes to knock each other down perfectly, except the dominoes are the fundamental properties of the universe, and one tiny misstep could throw everything off. Here's the issue. For inflation to work as described, the hypothetical Inflaton field, the driving force behind the rapid expansion, had to start with just the right amount of energy. Too much and space would have stretched so violently that no galaxies could form. Too little and inflation wouldn't have lasted long enough to smooth out the universe. Think of it like tuning a guitar string. If it's even slightly off, the music falls apart. Critics point out that getting these initial conditions just right feels suspiciously convenient, as if the theory is retrofitted to match what we observe today. And it's not just the starting point. The way inflation ends is equally delicate. The process called reheating, where the Inflaton field's energy transforms into the particles we know today, had to happen in a very precise way. If it was too abrupt, the universe would have been left a chaotic mess, too gradual, and matter wouldn't have clumped together to form stars and galaxies. This level of fine-tuning makes some researchers uneasy, raising the question, does inflation solve cosmic mysteries, or does it simply replace them with new ones? Supporters of inflation counter that fine-tuning isn't necessarily a flaw, it could be a clue. Just as the Goldilocks conditions for life on Earth led scientists to explore the anthropic principle, perhaps inflation's precise requirements hint at deeper laws of physics we haven't discovered yet. Some theories, like string theory, suggest that the Inflaton field might naturally settle into the right configuration among countless possibilities in a multiverse. In other words, what looks like fine-tuning to us could just be one slice of a much larger cosmic landscape. But here's the real sticking point. Without direct evidence for the Inflaton field or a clearer mechanism for how inflation started and stopped, the fine-tuning critique remains a shadow over the theory. It's a reminder that even our best ideas in cosmology are works in progress, subject to revision or even replacement if something more elegant comes along. What makes this debate so fascinating is how it reflects the scientific process at its best. Inflation may dominate the conversation now, but the fact that scientists are wrestling with its imperfections keeps the door open for surprises. After all, the universe has a habit of defying our expectations. Whether inflation's fine-tuning is a temporary hurdle or a fatal flaw is still up for grabs, and that uncertainty is what makes the search for answers so thrilling. Now, let's shift our gaze from the universe's explosive beginnings to its mysterious present, where another cosmic force is stretching space itself: dark energy. If inflation was the universe's dramatic opening act, dark energy might be its enigmatic finale. Both phenomena involve the rapid expansion of space, but are they connected or just cosmic coincidences? Here's what we know. Dark energy, discovered in the late 1990s, is the mysterious force causing the universe's expansion to accelerate today. Unlike gravity, which pulls things together, dark energy pushes space apart, and its influence grows as the universe gets bigger. Sound familiar? Inflation also drove space to expand exponentially, but in the universe's first fraction of a second. The key difference: inflation was a short, violent burst, while dark energy's effect is slow and steady, like comparing a sprint to a marathon. But could there be a deeper link? Some theorists speculate that dark energy might be a weaker, lingering remnant of the Inflaton field, the same energy that powered inflation. Imagine a campfire roaring to life and then fading to embers. The Inflaton field's fiery intensity would have been the campfire, while dark energy could be those faint, leftover embers, still warm but vastly diluted over billions of years. It's an enticing idea, but there's a hitch: the energy scales don't match. The Inflaton field was trillions of times more powerful than dark energy's gentle push. Bridging that gap would require new physics, perhaps even a rethinking of how fields evolve across cosmic time. Another angle ties dark energy to the vacuum of space itself. Quantum physics tells us that empty space isn't truly empty, it crackles with fleeting particles and energy. Could dark energy be the cost of this quantum activity, a pressure inherent to the fabric of reality? If so, it might share a philosophical kinship with inflation, which also arose from quantum fluctuations. Yet again, the numbers don't quite add up. The vacuum energy predicted by quantum theory is impossibly larger than what we observe from dark energy, a discrepancy so stark it's been called the worst theoretical prediction in physics. While the similarities between inflation and dark energy are tantalizing, the differences are glaring. Inflation was a singular event, finely tuned to sculpt the universe's structure, while dark energy operates on a timescale so vast it threatens to leave the cosmos cold and empty. One unified them under a single theory would revolutionize our understanding of space, time, and energy. But for now, the connection remains speculative, a puzzle wrapped in the enigma of dark energy's true nature. What's undeniable is how both phenomena force us to confront the limits of our knowledge. Whether linked or not, inflation and dark energy bookend the universe's story with expansion, begging the question, is the universe hinting at a grand pattern, or are we simply stitching together mysteries to make sense of the dark? The answer, much like dark energy itself, remains just out of reach for now. Turning our attention to the cutting edge of cosmic discovery, let's explore how modern technology is peeling back the layers of inflation's secrets. The quest to understand the universe's explosive infancy isn't just about theories, it's about building instruments precise enough to catch whispers from the dawn of time. At the forefront of this effort are next-generation telescopes like the Cosmic Microwave Background Stage 4, or CMB-S4 for short. This ambitious project, set to begin observations in the early 2030s, combines the power of multiple ground-based telescopes across Chile and Antarctica. Why these locations, high-altitude deserts and polar ice, offer crystal-clear skies, free from atmospheric interference, allowing scientists to study the cosmic microwave background, the afterglow of the Big Bang, with unprecedented detail. CMB-S4's ultra-sensitive detectors will map subtle temperature variations and polarization patterns in this ancient light, hunting for fingerprints of gravitational waves rippling through the infant universe. These waves, if detected, would be smoking gun evidence for inflation, showing how quantum jitters were stretched across space during that unimaginably rapid expansion. But Earth isn't the only vantage point. Space missions like the European Space Agency's proposed LightBird satellite aim to complement ground-based efforts. Slated for launch around 2030, LightBird will orbit beyond Earth's atmosphere, free from its distortions, to scrutinize the CMB's polarization across the entire sky. Its goal, to measure the faint B-mode polarization signal, a twisted pattern in the light that could reveal inflation's gravitational waves with even greater clarity. Think of it like tuning a radio to eliminate static. By combining data from space and ground telescopes, cosmologists hope to isolate inflation's signal from the cosmic noise. Meanwhile, quantum sensors are pushing the boundaries of what's measurable. Devices like superconducting gravimeters, once used to detect earthquakes, are now being repurposed to test theories of quantum gravity, a realm where inflation's mechanics might hide. And let's not forget supercomputers, which simulate the universe's first moments with staggering precision. These digital labs allow scientists to tweak inflationary models, predicting what signatures next-gen telescopes should hunt for. It's like reconstructing a crime scene, but instead of fingerprints, researchers look for imprints of quantum fields in the cosmos. Yet challenges remain. Distinguishing inflation's signal from later cosmic events like galaxy formation or interstellar dust requires painstaking data analysis. That's where machine learning steps in, sifting through petabytes of telescope data to spot patterns human eyes might miss. The marriage of AI and astronomy is transforming how we test inflationary theories, turning what was once speculative into something increasingly tangible. What makes this technological race so thrilling is its potential to bridge theory and observation. For decades, inflation has been a brilliant idea lacking definitive proof. Now, with tools like CMB-S4 and Lightbird, we're on the verge of answering whether our universe's grand beginning truly unfolded as inflation predicts, or if the cosmos has even deeper surprises in store. The next decade could rewrite cosmology's textbooks, proving once and for all whether inflation was the universe's opening act, or just one chapter in a far stranger story. Now, let's step beyond the labs and telescopes for a moment and see how cosmic inflation has sparked imaginations far beyond the world of science. The idea of a universe ballooning faster than light, birthing countless realities, isn't just textbook physics, it's fuel for some of the most mind-bending stories in science fiction. Take the multiverse, for example. Films like Everything Everywhere All at Once and TV shows like Rick and Morty run wild with the concept, weaving tales where every decision spawns a new universe. These stories borrow straight from inflationary theory, particularly the idea of eternal inflation, where bubble universes pop into existence endlessly, each with its own laws of physics. It's not just entertainment, it's a playful way to grapple with a dizzying scientific idea. Time travel gets a cosmic twist too. In Interstellar, the warping of space-time near a black hole echoes the extreme curvature inflation describes. Or consider Doctor Who, where the TARDIS dances through dimensions, a nod to theories like string theory, which inflation often ties into. These narratives don't just entertain, they make the abstract tangible, letting audiences feel the physics through storytelling. Even comic books get inflationary. Marvel's Secret Wars event collapsed and rebooted its multiverse, mirroring how some theories suggest our universe might recycle itself. DC's Crisis on Infinite Earths, that's basically a superhero take on bubble universes colliding. These plots aren't just random, they're rooted in real cosmological debates about whether our universe is unique or one of many. But pop culture doesn't just borrow from inflation, it shapes how we perceive it. When the Big Bang Theory, the show, not the event, cracks jokes about parallel universes, it's sneakily teaching millions about quantum mechanics. Neil deGrasse Tyson's Cosmos uses animation to show space stretching during inflation, turning equations into visual poetry. Even video games like No Man's Sky, with its procedurally generated galaxies, let players explore a universe that feels infinitely expansive, just like inflation predicts. Yet there's a catch. These creative spins sometimes blur the line between fact and fiction. Movies rarely mention that faster-than-light inflation refers to space itself expanding, not objects moving through it, a nuance even Star Trek glosses over. And while multiverses make great drama, they're still hypothetical. That's why the best sci-fi, like Arrival or Contact, balances wonder with real science, sparking curiosity without misleading. What's fascinating is how this feedback loop works. Scientists like Carl Sagan and Kip Thorne have advised Hollywood, ensuring the fiction respects the physics. Meanwhile, a teen watching Ant-Man might Google quantum realm and stumble on inflation research. Pop culture isn't just reflecting science, it's recruiting future scientists. So next time you see a Star Wars hyperdrive jump or a Loki timeline branch, remember, those ideas sprang from equations scribbled by cosmologists. Inflation isn't just shaping the universe, it's shaping our stories, our questions, and maybe even our future discoveries. Now, let's clear up some common confusions about cosmic inflation, because even the most mind-blowing theories can get twisted when they jump from textbooks to TikTok. One of the biggest mix-ups, the idea that inflation means things were moving faster than light. Here's the thing, it's not that galaxies or particles were zooming past light speed. Instead, space itself was stretching, carrying matter along for the ride. Think of it like dots on a balloon. As you blow it up, the dots move apart, but they're not actually traveling across the surface. That's why inflation doesn't break Einstein's rule that nothing can move through space faster than light. Another myth, that inflation contradicts relativity. Nope, general relativity actually allows space to expand at any rate. It's the motion of objects within space that's capped at light speed. This subtle distinction trips up a lot of folks, even in sci-fi. Remember when Interstellar showed planets orbiting a black hole? That time warp is rooted in the same physics that lets space stretch during inflation without violating relativity. Then there's the oversimplification that inflation caused the Big Bang. It's more accurate to say inflation happened immediately after the Big Bang, smoothing and stretching the universe in a fraction of a second. Imagine tossing a handful of glitter into the air. The Big Bang is the toss, and inflation is the gust of wind that spreads the glitter evenly across the room. Without that wind, you just have a clumpy mess. Some critics also claim inflation is untestable, a just-so story. But the cosmic microwave background, our baby picture of the universe, shows temperature patterns that match inflationary predictions with stunning precision. It's like finding a fossil with exactly the right features to confirm an evolutionary theory. And while we haven't yet spotted primordial gravitational waves, the smoking gun for inflation, telescopes like CMBS-4 are actively hunting for them. Finally, pop culture loves to conflate inflation with dark energy. Both involve expansion, but dark energy is the current, slow-motion version, like hitting cruise control on the universe's growth. Inflation was the explosive pedal to the metal moment at the start. Mixing them up is like confusing a firework with a candle. The bottom line, inflation is weird, but it's not magic. It's a rigorously tested framework that solves real puzzles, like why the universe looks so uniform while leaving room for mysteries we're still unraveling. And that's what makes it so thrilling. But here's the exciting part: cosmic inflation isn't just a story about the distant past. Scientists are racing to test it with cutting-edge tools that could rewrite our cosmic playbook. One of the most anticipated experiments is the next generation of gravitational wave detectors. These aren't your everyday telescopes. They're designed to catch ripples in space-time itself, echoes from the universe's first moments. If inflation really happened, those ripples should carry a faint fingerprint, a specific pattern called B-mode polarization in the cosmic microwave background. Projects like CMBS-4, a mega collaboration of telescopes in Chile and the South Pole, are scanning the sky for this telltale signal. It's like trying to hear a whisper in a hurricane, but the payoff could be huge. Then there's the Laser Interferometer Space Antenna, or LISA, set to launch in the 2030s. This space-based observatory will hunt for gravitational waves at frequencies too low for ground detectors to pick up. Imagine tuning a radio to a station no one's ever heard before. LISA could reveal cosmic events from the inflationary era, like collisions of primordial black holes or even defects in space-time left over from the universe's rapid expansion. But it's not just about gravitational waves. Particle colliders are joining the chase too. Some theories suggest the Inflaton, the field that drove inflation, might leave traces in high-energy particle collisions. Machines like the Future Circular Collider, a proposed successor to the Large Hadron Collider, could smash particles with enough energy to recreate conditions eerily close to the inflationary epoch. It's a long shot, but finding even a hint of the Inflaton would be like stumbling on a fossilized dinosaur bone in your backyard. And let's not forget quantum sensors. These ultra-precise devices, some chilled to near absolute zero, might detect subtle shifts in gravity or spacetime that hint at inflation's aftermath. Teams are already testing prototypes in abandoned mines and underground labs shielded from cosmic noise. It's detective work on a cosmic scale, piecing together clues 13.8 billion years cold. Of course, not every experiment will pan out. Some might deliver surprises that force us to rethink inflation altogether. That's the beauty of science. The universe gets the final say. But whether inflation stands or falls, these missions are pushing us closer to answering the ultimate question. How did everything we see and everything we are come to exist? The next decade could deliver answers we can't even imagine yet, and that's why the hunt is worth every ounce of effort. Now, let's step back and consider the bigger picture. What does cosmic inflation really tell us about time itself? One of the most profound questions it raises is whether the universe had a definitive beginning or if time is part of an endless cycle. Inflation suggests a sudden, explosive origin, but some theories propose that our universe might just be one chapter in an infinite cosmic saga. Imagine a book where each page is a new universe born from the collapse or collision of a previous one. This idea, known as cyclic cosmology, challenges the notion of a single Big Bang, painting time as a loop rather than a straight line. Then there's the haunting question of what existed before inflation. If time as we know it began with the universe, asking what came before might be like asking what's north of the North Pole. But some physicists argue that quantum fluctuations or a multiverse landscape could mean our universe is just one bubble in a vast, eternal foam of reality. It's a dizzying thought that our entire cosmic history might be a tiny blip in an unfathomably larger structure. But why does this matter? Because how we view time shapes how we see our place in the cosmos. If the universe had a clear starting point, it implies a narrative with a beginning, middle, and possibly an end. But if time is cyclical, everything we know, galaxies, life, even the laws of physics, might recur in some form forever. It's the difference between seeing existence as a unique story or a verse on repeat. And what about us? In an inflationary universe that may be one of countless others, humanity's significance seems to shrink, or does it? Some argue that a multiverse amplifies our curiosity. After all, we're the part of the cosmos that's awake, asking these questions. Whether we're alone or one of infinite observers, the fact that we can ponder these mysteries might be the most remarkable thing of all. These ideas aren't just abstract musings, they guide how scientists design experiments. If the universe is cyclic, for example, we might search for faint imprints of a previous cycle in the cosmic microwave background. If it's part of a multiverse, the peculiar constants of nature, like the strength of gravity or the mass of an electron, could hint at siblings beyond our cosmic horizon. Ultimately, inflation doesn't just explain how the universe expanded, it forces us to confront what beginning even means. Whether time is linear, circular, or something stranger, one thing's certain: the answers, if we find them, will redefine reality itself. And that's a journey worth taking together. Now let's turn our gaze outward. What does cosmic inflation mean for the possibility of life beyond our own universe? If inflation gave rise to a multiverse where countless bubble universes exist with different physical laws, the search for alien life takes on a whole new dimension. Imagine each bubble as a separate cosmic experiment, some with gravity too weak for planets to form, others with chemistry so chaotic that complex molecules never stabilize. In such a landscape, the conditions for life might be rare or astonishingly common, depending on how many bubbles land in the Goldilocks zone of physics. Here's where it gets fascinating. Our universe's constants, like the strength of electromagnetism or the density of dark energy, seem finely tuned to allow stars, planets, and ultimately life. But if other bubbles have different rules, some might permit life in forms we can't even imagine. Picture a universe where time flows backward, or where dark energy dominates so fiercely that galaxies never coalesce. Life in those realms would face entirely different challenges or opportunities. This raises a provocative question. Could alien life exist in a universe where, say, carbon doesn't bond the way it does here? Some scientists speculate that in universes with stronger nuclear forces, silicon-based life might thrive, or that exotic energy fields could sustain consciousness without planets or DNA. Others argue that without water, stable atoms, or predictable thermodynamics, life as we define it would be impossible. The multiverse could be teeming with civilizations, or eerily silent, with ours as a fluke in a vast desert of uninhabitable realities. But let's not forget the wild card. Intelligence might not be the pinnacle everywhere. In a bubble where entropy operates differently, evolution could favor perpetual simplicity over complexity. Or perhaps life is abundant, but communication across universes is fundamentally impossible, leaving each bubble forever isolated. The chilling truth is that even if the multiverse is infinite, we might never know if we're alone. Yet there's hope. If inflation's gravitational waves leave imprints in the cosmic microwave background, or if future telescopes detect anomalies in the sky that hint at neighboring bubbles, we could find indirect clues of other universes, and by extension, other life. It's a long shot, but science thrives on long shots. Ultimately, inflation doesn't just reshape our cosmic address, it reframes the very meaning of life. Whether we're a rare accident or one of countless civilizations, the search for answers continues. And who knows, the universe next door might be staring back at us, wondering the same thing. Now, let's bring this cosmic phenomenon down to Earth with some everyday comparisons that make inflation easier to grasp. Think of the universe like a loaf of raisin bread baking in the oven. Before it goes in, the raisins representing galaxies are all clustered close together. But as the dough expands uniformly in the heat, every raisin moves away from every other raisin, with no single point as the center. That's exactly how cosmic inflation works. No matter where you are in the universe, everything appears to be moving away from you, not because you're special, but because space itself is stretching evenly everywhere. Another useful analogy is a balloon with dots drawn on its surface. As you inflate the balloon, each dot grows farther apart from its neighbors. The dots aren't moving across the surface, they're being carried apart by the stretching material. Replace those dots with galaxies and the balloons rubber with space-time, and you've got a snapshot of cosmic inflation. What's wild is that this expansion isn't limited by the speed of light, since it's space itself changing, not objects moving through space. For something more tactile, picture a rubber band with marks spaced evenly along its length. Stretch it gently, and the gaps between the marks grow uniformly. Now imagine that rubber band stretching so fast that tiny quantum jitters imperfections in the marks get blown up to enormous scales. Those jitters are like the quantum fluctuations during inflation, which eventually became the seeds for galaxy clusters. It's mind-bending to think that the largest structures in our universe trace back to subatomic tremors magnified by inflation. Even sound can help visualize this. Play a single note on a synthesizer and then slow it down drastically. The pitch drops as the sound waves stretch. Inflation did something similar to the universe's earliest notes, stretching primordial ripples into the vast cosmic web we see today. The beauty of these analogies is that they strip away the abstraction, showing how inflation isn't just a theoretical idea. It's a physical process with consequences we can observe. Whether it's bread, balloons, or sound waves, everyday experiences help bridge the gap between the unimaginably large and the intimately familiar. And that's the power of a good analogy. It turns "wait, what?" into "oh, I get it now." Now, let's shift gears and consider some of the critiques that challenge cosmic inflation. While it's a leading theory, not all scientists are convinced it's the full story. Take Roger Penrose, for example, a Nobel Prize-winning physicist who argues that inflation might not be the only answer. He proposes something called conformal cyclic cosmology, a mind-bending idea that suggests the universe goes through endless cycles of expansion and contraction with no true beginning or end. In this model, what we call the Big Bang might just be one chapter in an infinite cosmic saga, where each cycle leaves subtle imprints on the next. Penrose isn't alone in his skepticism. Some critics point out that inflation requires incredibly precise initial conditions to work, conditions that might seem too fine-tuned to be plausible. Imagine setting up a domino chain where each piece must fall at just the right angle to keep the cascade going. If even one domino is slightly off, the whole thing collapses. Inflation's critics argue that the theory relies on a similarly delicate balance, raising questions about whether it's the most elegant explanation. Others highlight the lack of direct evidence for the inflationary field, the so-called inflaton. While inflation explains many cosmic puzzles beautifully, we've yet to detect this hypothetical field or its particles. It's like solving a mystery with a suspect that no one has ever seen, compelling but leaving room for doubt. Then there's the issue of falsifiability. A good scientific theory should make predictions that can be tested and potentially proven wrong. Some argue that inflation is so flexible it can accommodate almost any observation, making it hard to disprove. If a theory can explain everything, does it really explain anything? That's the thorny question skeptics wrestle with. But here's the thing: science thrives on debate. These criticisms don't mean inflation is wrong. They mean it's being rigorously tested. Even Penrose's cyclic model has its own challenges, like explaining how the universe resets between cycles without losing all its structure. The beauty of cosmology is that every critique pushes us closer to the truth, whether it confirms inflation or leads us to something entirely new. After all, the universe owes us no easy answers, just endless mysteries to unravel. Now, stepping back to take in the bigger picture, let's appreciate just how profoundly cosmic inflation has reshaped our understanding of the universe. Before inflation came along, cosmology and particle physics seemed like distant cousins, one studying the vast cosmos, the other probing the tiniest particles. But inflation bridged that gap, showing how quantum mechanics, the rules governing the subatomic world, could leave fingerprints on the entire universe. It's as if we discovered that the same brushstrokes paint both the microscopic and the cosmic canvas. One of inflation's most groundbreaking legacies is how it wove gravity into the fabric of particle physics. Einstein's general relativity described gravity as the curvature of spacetime, but inflation gave us a new lens to see how gravity interacts with quantum fields during the universe's infancy. The Inflaton Field, though still hypothetical, represents a missing link, a scalar field that could unite these two pillars of physics. Think of it like uncovering a hidden chapter in a grand epic, one that ties together seemingly unrelated plot lines into a cohesive story. Inflation didn't just solve cosmic puzzles, it rewrote our origin story. Before the 1980s, the Big Bang was the opening scene, full of heat and energy, but lacking an explanation for the universe's smoothness and structure. Inflation filled in those gaps, proposing a dramatic prelude where space expanded exponentially, smoothing out wrinkles and planting the seeds for galaxies. It's the difference between seeing a finished sculpture and finally understanding the sculptor's tools and techniques. Critically, inflation also showed us that the universe's large-scale features might trace back to quantum fluctuations, tiny, random variations in energy that were stretched to cosmic proportions. This idea alone has inspired decades of research, from simulating the early universe in supercomputers to hunting for primordial gravitational waves. It's a testament to how one bold idea can ripple across an entire field, sparking new questions and technologies. Yet perhaps inflation's greatest gift is its humility. By suggesting that our observable universe might be just one bubble in a vast multiverse, it reminded us how much we still don't know. That's the mark of a truly transformative theory. It doesn't just answer questions, but opens doors to even deeper mysteries. Whether inflation stands the test of time or gives way to something new, its impact on physics is undeniable. It taught us to see the universe not as a static stage, but as a dynamic, ever-evolving story, and that's a legacy worth celebrating. Now, let's turn the spotlight to you, because cosmic inflation isn't just a story for scientists. It's a puzzle we can all ponder together. Imagine for a moment, If our universe is just one bubble in an endless cosmic foam, could we ever catch a glimpse of another? The idea isn't as far-fetched as it sounds. Some theories suggest that if another bubble universe collided with ours, it might leave faint imprints in the cosmic microwave background, like ripples from a pebble tossed into a pond. But here's the catch: those signals would be incredibly subtle, buried in noise. So what do you think? Would such a discovery shake your understanding of reality, or would it feel like just another piece of the grand cosmic puzzle? Speaking of puzzles, let's tackle another head-scratcher. If inflation stretched quantum fluctuations into galaxy-sized structures, does that mean everything around us, stars, planets, even you and I, trace back to random quantum jitters? It's a humbling thought, isn't it? One moment subatomic chaos, the next the ordered beauty of a spiral galaxy. But here's where it gets even wilder. If the Inflaton Field's energy had dipped slightly differently, those fluctuations might never have grown into anything at all. So, do you see this as pure chance, or does it hint at something deeper, like a universe fine-tuned for complexity? And let's not shy away from the elephant in the room, the multiverse. If inflation truly spawned countless bubble universes, each with its own laws of physics, what does that mean for the uniqueness of our existence? Are we just one outcome in an infinite tapestry of possibilities, or is there something special about our particular cosmic neighborhood? Some argue that the multiverse explains why our universe seems so perfectly suited for life, because in an infinite ensemble, even the rarest conditions must arise somewhere. Others find the idea unsettling, like swapping a carefully crafted story for a library of random drafts. Where do you stand? Finally, let's bring it back to Earth. If inflation reshaped the cosmos in a fraction of a second, could we ever recreate such extreme conditions in a lab? Particle colliders like the Large Hadron Collider can't reach inflation's energy scales, but some researchers speculate that tabletop experiments with ultra-cold atoms might simulate aspects of inflationary physics. It's a long shot, but imagine the implications: a window into the universe's first moments, right here on our planet. Would that be the ultimate scientific triumph, or just the beginning of even bigger questions? Your thoughts are part of this journey too. Drop a comment below. Do you think we'll ever crack inflation's deepest secrets, or will they remain just beyond our grasp? And while you're at it, don't forget to hit like and subscribe for more cosmic adventures. The universe is full of mysteries, and together we're just getting started. As we wrap up this cosmic journey, let's take a step back and marvel at just how much inflation has reshaped our understanding of the universe. In a fraction of a second, this rapid expansion not only smoothed out the cosmos, but also planted the seeds for everything we see today: galaxies, stars, even the conditions that made life possible. It's like the universe's ultimate magic trick, stretching a speck into a vast, structured tapestry. Yet for all we've learned, inflation leaves us with tantalizing gaps. Why did it start? What triggered it? And if it truly happened, what came before? These aren't just scientific questions, they're philosophical ones, inviting us to ponder the very nature of existence. The beauty of inflation lies in its echoes. Every time we look at the cosmic microwave background, we're glimpsing those first moments frozen in time. Those subtle temperature variations, they're the fingerprints of quantum fluctuations stretched across the sky. And while we've pieced together much of the puzzle, the full picture remains elusive. Are primordial gravitational waves hiding in the CMB's B-mode polarization, waiting to confirm inflation beyond doubt? Could future telescopes like CMB S4 or next-generation space observatories finally catch them in the act? The hunt is on, and every new discovery brings us closer to answers, or perhaps to even bigger questions. Then there's the grandest mystery of all, the multiverse. If inflation never truly stopped, but instead created countless bubble universes, what does that mean for our place in the cosmos? Are we one of many, or is there something uniquely special about our universe's recipe? It's a humbling thought, one that blurs the line between science and speculation. And while some dismiss the multiverse as untestable, others see it as the next frontier, a challenge to push the boundaries of what we can observe and imagine. So, where does this leave us? Inflation has given us a framework, a story that ties the universe's birth to its present grandeur. But like any good story, it's filled with twists and open-ended questions. What do you think lies beyond the edges of our cosmic bubble? Could there be other versions of reality, or is ours the only one that ever was? Drop your wildest theories in the comments below. I'd love to hear what sparks your curiosity. And if you've enjoyed this dive into the universe's first moments, don't forget to like, subscribe, and hit that notification bell. The cosmos is full of wonders, and together we're just scratching the surface. Until next time, keep looking up.